In this video, I want to talk about factoring polynomials using formulas. First of which is the difference of squares formula, and I also wanted to talk about the differences of cubes, sum of cubes, and a few others. But all of these factoring formulas are in your book. We talked a little bit about why they're true in class, but basically these are sometimes referred to as algebraic identities because it represents a fact about if I have x plus y times x minus y, that always will multiply out to be x squared minus y squared due to the cancellation of the inner products. And it just emphasizes a particular way that something will behave if we have that structure. But we can use that fact to also factor. Like if I have a difference of squares, what I know is it must always factor in this particular way. Same with difference of cubes and sum of cubes. But sometimes it's a little bit trickier, like in these particular cases. Like for example, in this one, what I always recommend is thinking about, okay, if it is two terms, usually we want to resort to one of these formulas. But I would recommend thinking about, well, what is the base of the square? Like here, I can see that this is a square and 169 is 13 squared. Might not be one you have memorized, not a big deal. But basically another thing I wanted to warn you about is that if you have a leading coefficient, you can't just ignore that. That's part of it as well. And again, you could factor this by magic X method, but it's going to be a whole lot easier to use the formula. But so what I recommend here is to rewrite it as, if I'm going to use this formula, I need to have it exactly as is. I need the first thing to be squared and the second thing to be squared. But here, notice that only the x is written as a square. 9, while it is a square, is not written that way. But basically what I would recommend is writing it as parenthesis 3x squared, right? Because 9 is really just 3 squared. So that whole term I could write as a square. And then 169 is 13 squared. And if I write it that way, now it's a little bit easier to see, well, what is x and y in this associated situation? And once I write it as a true difference of squares, because this one wasn't exactly written the right way, if you see what I mean, now I know x and y, and now I could apply the factorization. And a difference of squares always factors as the first plus the second times the first minus the second. So 3x plus 13 times 3x minus 13. And the point of having the formulas is it's just so much easier to figure out. I don't have to go through a magic X method or some other method to figure out how to factor a difference of squares. Because notice it will just work out. 3x times 3x obviously makes 9x squared. 13 times negative 13 obviously makes negative 169. And since it's the same on both, one's positive, one's negative, those inner products will cancel each other out, because this would give me negative 39x, where this one would give me positive 39x. And very similar train of thought for difference in sum of cubes. Like with this one, I can tell both of those are cubes, but in the same way, the second one is 2 parts. So I would want to rewrite that as a cubed minus 125 is 5 cubed. So I'd want to write that as 5b in parentheses cubed, because that's equivalent. And then I could apply the formula, which is right here, which would give me the first minus the second, a minus 5b. And then that would be times this whole thing over here, x squared, which in our example, x is a. If this is a little bit hard for you to do, what might be helpful is just kind of to note to yourself, okay, this is going to be x based on the formula right there. And then this is going to be my y. And sort of use it as a substitution replacement. And then over here, plug it in the same way, right? So each of those y's will be plugged in there, there, and there. And each of the x's will be plugged in here, here, and here. And that's where I'm going to get the following stuff. So x minus y is just red minus green. And then I'm going to have red squared, which is a squared, minus xy, which is just the 2 times each other, which would be 5ab. And then plus green squared, which would be 5b squared. So that would actually make 25b squared. But this would give me the factorization of the difference of cubes. Definitely a little bit harder, but if you catch my drift, it's just applying the formula in a very similar way. It's just a more complicated formula, just because difference of cubes is a little bit more difficult. And when it comes to what we call a perfect square trinomial, let's go ahead and just skip this one because you could always factor those just using a magic X. But let's also look at the sum of cubes, which in the same way, since it's starting with 8 here, I would rewrite this as 2x parenthesis cubed. And 1 technically is a cubed as well, because 1 is actually a square, a cube. It's any power of itself. So that being said, if I wanted to translate this into and factor this expression, sum of cubes can always be factored using this formula. Unlike a sum of squares actually have no possible factorization. Well, technically that's not true. You can using imaginary numbers, but no real factorization. Whereas sum of cubes always will work as follows. So it would always be the first plus the second times the first squared minus the 2 times each other, and then plus the second squared. And that should give me the proper factorization for a sum of cubes. And as always, you can multiply them all out to make sure it works and makes the original. But if you're following the formulas, these formulas are unilaterally true. And that's what we mean by an algebraic identity. An algebraic identity is just a truthful mathematical equation. It doesn't matter what you plug in, it always works. And that's kind of the way we can use an identity to help us factor.